find that I can sort of kind of get used to teaching my class remotely, but it's just not the seminars are just not the same. I don't know, just to me, it's just not the same if you're not there in person. So
yeah. Okay. Well, we'll get started. Welcome everyone for our continuing seminar series in physics. Today's guest is a name that some people might recognize, Unruh, as in the Unruh Scholarship that we offer here at Wichita State, named after Carl's parents. Henry Unruh was a professor of physics and chairman of physics here at Wichita State for a while, and they gave a gift of an endowed grant for us to give out scholarship money every year to physics majors. And Carl is a very distinguished professor of physics at the University of Delaware, specializing in solid state physics. And today he's going to be talking to us about ultra fast optical pump X-ray measurements. So welcome.
okay, well, thank you all. Thank you very much for inviting me. I appreciate the opportunity to with some caveats that I will put out as we go on. But what I'd like to, to get started then, what I'd like to say is that there are about, there are basically two main goals or objectives I have, hopefully in the next 50 minutes or so to achieve. And one of them, and the first one, and maybe the most important one, is that just to emphasize that in the last more than 100 years now, since the first X-ray diffraction patterns were first acquired, that advances in technology and computers and facilities have led to just incredible advances in the way one can do what is historically a really old measurement, that is to say, to probe the structure of matter with X-rays. And in particular, what I want to introduce you to is the idea of time-resolved X-ray diffraction measurements, in which basically we can now are in a position where we can acquire diffraction measurements with time resolutions, well, depending on the facility you go to, but as short as about 10 femtoseconds. So we now have the capability to make diffraction patterns that are snapshots of matter on timescales of the fundamental timescales that characterize solid matter itself. So in some sense, we can make movies of atomic vibrations, given if you with the correct facility. So that's my global mission, is to try to introduce you a little bit to that kind of technology and the capabilities that provides. But then to actually provide an example of that with some work that me and my colleagues are interested in, which is to apply this kind of a measurement technique to study irreversible as well as reversible processes, and that are taking place in nanostructured materials. So I want to make a little bit of a disclaimer here to start with. You'll see as we go forward that these measurements are all done at a national laboratory. They've been done at the Advanced Photon Source at Argonne National Laboratory. And we were scheduled to be there in the February 2020 for a run. That run was canceled. We haven't been back in more than a year and a half now. And so what I'm going to show you is, on the one hand, incomplete, and on the other hand, unfortunately, is not all that up to date. But there's not a lot I can do about that at this point. And so with that caveat, let's try to get started. So these are the things that I actually wanted to actually go over. Almost every talk I ever give starts off with some slide that deals with time scales and length scales. And I want to do that in this talk as well. And then what I want to do by way of background and motivation is to talk a little bit about time-resolved X-ray diffraction and try to emphasize the difference between the old way of doing things, or the traditional way, which is to acquire pictures of matter, and the new way, or at least a new version of the old way that can make movies of how structures evolve in time. And then I'm going to just try to put those two pieces of information back together to provide what my initial thought was to motivate why it might be interesting to study irreversible structural transformations in nanostructured materials. So that'll constitute a background and a motivation. Then what I want to do is I want to talk about the technique of ultrafast time-resolved X-ray diffraction and the implementation of that technique in a method called optical pump X-ray probe. And then sort of, because it's going to play a little bit of a role going forward, I want to emphasize some kind of issues that are associated with doing that with ultrafast time resolution. This is associated with the kind of beams that are being produced at the synchrotrons where we did this work. Then I want to talk about the first efforts that took us down this path, mainly the study of gold-platinum multilayers. And while that illuminated quite a lot of interesting physics, at least in our mind, it also pointed out some complications that we completely overlooked when we started this effort and then had to be dealt with. That led into the latest work that we did pre-COVID, which was the development and the installation of what we call a tunable multi-layer monochromator, and to use it in a set of trial measurements on lattice relaxation in thin films of platinum. So that's sort of where I want to go, ending up with a little bit of a summary, a few statements about what we're sort of doing going forward, and then to acknowledge, I hope, everybody who has contributed to this. Let me just say that if you're comfortable with that, I'm more than comfortable being interrupted at any time. If people have questions or clarifications or anything that I can help with, you're more than welcome to do that. But if not, I'm hopefully trying to target about a 50-minute talk. And so there should also, I hope, at least be some time for questions at the end if there actually are. Okay, so let's talk about length and time scales. And basically the observation here is that the universe is a very big place. And it ranges, depending on how you want to measure, from a Planck scale to the size of the universe itself. So this Planck scale is just an exercise in dimensional analysis. It's the way you can put together fundamental constants to get the dimension that you might be interested in. And if you do that in a way to produce a length, the Planck scale is something at the order of 10 to the minus 35 meters. That's to be compared to the size of the universe, which is about 10 to the 26 meters. And in between those two length scales, the length scale of about 1 angstrom, or 10 to the minus 10 meters, provides a kind of crude, rough, approximate demarcation between the kind of phenomenon the physical world exhibits. On the one hand, on smaller length scales, quantum phenomenon with its characteristic uncertainties, its characteristic quantization, and on the length scales larger than that, classical phenomenon, which is the regime of Hamilton's equations and electrodynamics and things like that. So this length scale is characteristic of interatomic distances in matter. All right, now, if you don't like lengths, you prefer times, that's easy enough because all you have to do is divide by the speed of light. And that gives you a Planck scale in terms of seconds of about 10 to the minus 44 seconds, and the age of the universe of about 10 to the 17 seconds. Now, intermediate here between these two length scales is a length scale that goes from femtoseconds, as I've characterized it, to nanoseconds. And this is the characteristic time scales that are associated with a variety of really basic and fundamental and interesting phenomenon in matter. They are, for example, the time scales that are associated with energy transfers in molecules. They're the time scales that are associated with how electrons are moved around when you do chemical reactions. They are the time scales that are associated with lattice dynamics. That is to say, the time scale upon which the atoms that make up solids vibrate, and a whole host of phenomena that appear at this time scale. So this is a very interesting time scale. And the takeaway message of this is that while everybody knows that X-rays have small length scales on the order of 10 to the minus 10 meters, and therefore are useful for probing interatomic distances, it's only been relatively recently that people have realized that by an appropriate experiment, you can use these same X-rays to probe physical phenomenon that are happening on very small time scales as well. So the takeaway message, if nothing else, right up front, is that X-rays can be used to probe both small length timescales and small timescales. Okay, so a little bit of history about that. It's kind of interesting that the discovery of X-rays apparently is known to the day. It was November 8th, 1895, when William Röntgen was playing around with what were then called Crookes tubes, and realized that in addition to optical light that were being emitted from them, they were emitting something which he had no idea what it was, so he called them just called it X radiation that was highly penetrating. I find it kind of interesting to note that what everybody has seen is some of the first X-ray images that were made of a hand, showing the bone structure and some kind of the flesh and a ring on the hand. Apparently, the first ones of those that were made with Röntgen's wife. And I always thought this was kind of an interesting to think about, that he was seeing this unknown radiation that he had no idea what it was. So his first thought was to get his wife to put his hand in it and see if they could see anything interesting that came out of that. In any case, it was quite a while before that radiation was realized to have very short wavelengths. And this is one of the first X-ray diffraction images that was ever produced. This came from the famous paper in 1912 that was carried out by Friedrich and Knipling, with the suggestion of Max van Laue. And so this already is a very high quality diffraction pattern and is quite amazing in just what it shows. Up to this day, this Crookes tube is basically the same technology that's used in modern day X-ray tubes that appear in my lab and scores of labs at the University of Delaware and everywhere else. And their characteristic feature is that they produce continuous X-rays and that they produce X-rays on just a routine basis without any problem at all. So you spend $100,000 or $200,000, you can buy a modern laboratory X-ray diffractometer. They will use X-ray tubes like this. If you spend another $100,000, you can buy a fancy detector that will give you time resolution of the order of 10 milliseconds, but usually that's not done. And so this kind of X-ray diffraction experiment is what has been done now for more than 100 years. But starting in the middle 1990s, there was a new generation of experimental facilities that started coming online, and they're called third generation synchrotrons. They are inevitably national facilities. They cost about $1 billion each. And what they do, unlike the traditional X-ray diffraction, the traditional X-ray sources and X-ray diffraction measurements, is to produce not only extraordinarily intense beams of X-rays, but also to produce them in extremely short pulses. So synchrotrons are called third generation machines, whereas a variation on that same theme, which are called X-ray free electron lasers, are also national facilities, even at a bigger scale. And they also produce very, very intense X-ray pulses, but also very short. So the characteristic of these facilities is that they appear as national facilities. They're expensive to do. They're very expensive to maintain and to run, but they produce pulse X-rays at third generation synchrotrons with a time duration between typically 10 and 100 picoseconds, and at free electron lasers or XFEL facilities with time lengths of 10 femtoseconds, maybe even shorter, depending on how you push the experiment. Okay, so what can you do with that? So 4 or 5 years ago, I was getting bored at the kind of work that I was doing at the time, which was to study phase transitions, to study to do thermodynamic measurements, magnetic measurements, and a little bit in the way of transport in nanostructured materials. And I was starting to think about something new to do. And I was fortunate at that time because my next door neighbor in the physics department is an expert on ultra-fast lasers and their applications, and has a long history of working at Argonne National Laboratory using ultra-fast laser techniques. And so when we were talking about this over extended period of time, many coffees, many beers as well, we started thinking that it would be interesting to try to study atomic transport when it takes place irreversibly with sub-nanosecond time resolution. So really there has been sort of a trend in that area of starting with studying diffusion, new phase formation in bulk materials, and then progressing to nanostructured materials like thin films and multilayers, and then down into zero-dimensional materials. But none of these measurements have been carried out with time resolution, and we thought that that might be interesting to do. So at that time, my semi-quantitative argument was for doing this was this. Now, it turns out that, in fact, I don't really believe this argument anymore, but this was the argument that I was sort of selling at the time. And that is that if you think about a description of solid state diffusion as basically a differential equation, this is called fixed second law, that tells you how a composition profile evolves in time and in location. And you carry out what's called a Boltzmann transformation, where you make a new variable that is the position of in a sample where the composition is measured and the square root of the time. You transform to a differential equation that only depends on lambda. And what this tells you is that x has to be proportional to the square root of the time, because that's the scale that was introduced when you made the transformation. And if you differentiate this, you get a speed with which a front of constant composition moves that scales like 1 over the time, which suggests that if you go to very early times, the velocity diverges, and so the whole argument has to break down. And therefore, we thought it would be interesting if we could actually probe this very early times and to try to probe in as much detail as we could the breakdown in fixed second law. Okay, so like I said, people are interested. I don't think this is a particularly valid argument anymore, but that was sort of my initial thinking. And so we posed this question: would it be possible to study solid state diffusion, irreversible structural transformations that are associated with the motion of atoms on ultra-fast time scales, and to do it in nanostructured materials? Would there be anything interesting to learn about there? And so that was basically our motivation. Okay, so we had some background in this already, and I'll just give you a little bit of that. So we have quite a bit of experience in building nanostructured materials. So for example, in the first instance, in chemically preparing core shell nanoparticles, where we have elemental metal cores surrounded by elemental metal shells, and then heating these up a little bit, allowing the two to intermix, then more and more and more, and mix to a final alloy state. So this is an irreversible process in most cases. And we were already making these kind of samples and doing these kind of diffraction measurements without time resolution, and we thought they might be able to be extended into the ultrafast regime. And on the same way that we'd studied, we were making pretty high quality thin film multilayers with the same kind of story in mind. So this was an early just SEM image, a composition map of the kind of things that we are doing. These are copper cores surrounded by nickel shells, which are clearly seen in the image. These are big nanoparticles, so to say, but we only made this set big because they're much easier to image. We can make them the same thing, much smaller. And this is a TEM cross-sectional image of a platinum nickel multilayer, where you see the repeat length of 5 nanometers very accurately reproduced. So we have some experience from the sample fabrication standpoint, and therefore thought we might have a little bit of a heads up to move this into the ultrafast domain. So not only had we made them, but we'd done some measurements. So this is what I would call an ultra slow time resolved measurement, where we take those copper core nickel shell nanoparticles. I would put them in my in-house laboratory diffractometer in a furnace. And what we do is we ramp the temperature at about 10 degrees per minute. Then we lock the temperature at each one of these intervals, and over a 5-minute period of time, grab a diffraction pattern. So the qualitative features of this are just what you would expect. That basically there's no atomic motion, there's no evolution in the X-ray diffraction pattern up to about 350 degrees. But above that, you see a relatively rapid evolution in the diffraction pattern as the copper and the nickel atoms intermix, leading at sufficiently high temperature to a single phase alloy of the copper and the nickel. That would be what you would observe here. So the idea was, can we move something like this into the ultrafast regime? Okay, so how to do that? And so I want to make a digression on basically how one would approach doing that kind of a measurement. And there are basically two ways you can try to do a time resolved measurement if you want to do it ultra fast. One of them is that you illuminate your sample with a continuous source of X-rays, but you build a detector that is gated in a way that you can just sample a small subset at the fastest rate possible of the X-rays that are scattered by the sample. So this approach I would call continuous X-rays fast detector. And that means that basically what you have to do is be able to gate this detector and read it out in the fastest way you possibly can. So if you're interested in doing this on a time scale of about 1 millisecond, you can buy a box to put on your laboratory diffractometer in your own lab for between $50,000 and $100,000. But if you want to go faster than that, you need specialized detectors. And one of the things that we're working on, although I won't mention it at this point, is sort of collaborating with the detector group at Brookhaven National Laboratory, who are building detectors that can be read out to provide 1 nanosecond time frames. I just point out that this process is essentially an electrical process. That is to say, you have to move electrons, the electrons that are generated from the interaction of the photons that are scattered, the X-ray photons that are scattered into your detector, into electrons. You have to read them out as fast as you possibly can. Now, the other way to get time resolution is to use a slow detector, but to use pulsed X-rays. Okay, so the picture here is to generate not a continuous line of X-rays, but single pulses or groups of X-rays, scatter them off the sample and put them in the detector. And now you don't really care whether the detector is fast or slow, because all the information is carried in this small interval of time. And if you open the detector and read it out over a longer period of time, it still just contains the information that it was in this one pulse. So the key here is to be able to produce the short isolated pulses that allow this to happen. As I mentioned earlier, state-of-the-art facilities can produce pulses that are about 10 femtoseconds in length. And at least in the case of third-generation synchrotrons, the process by which these individual pulses are produced is essentially mechanical. This is sort of an interesting observation that it is sophisticated and expensive and difficult, but at the end of the day, it's just basically mechanical as opposed to electrical. Okay, so how do we do that? This is the way that we're going to do it. So the first thing is you go to Chicago or any number of other 30 or 40 other places on Earth. And at Argonne National Laboratory, they have a user facility there that's known as the Advanced Photon Source. So what it is a third generation electron storage synchrotron. It's 1,104 meters in circumference. It stores 7 GeV electrons. And for all practical purposes, that means those electrons are moving at the speed of light. It's just C minus epsilon. This is literally the right answer for how fast the electrons are moving. Now, not only do you put the electrons into this ring at relativistic speeds, but due to the cleverness of these synchrotron designers, what you can do is you can bunch them. They don't appear as a continuous current. They occur as bunches. And in the most common operating mode at the Advanced Photon Source, what is done is they're bunched up into 24 equally spaced bunches in the ring. Each one of the bunches is about 3 centimeters in length, and each bunch is separated from the next bunch by 46 meters. Now, because these electrons then are highly relativistic, what happens is that they radiate synchrotron radiation into an extraordinarily narrow beam of electrons from the accelerated electrons, a beam of photons. So it turns out that this beam angle here is approximately equal to 1 over the relativistic factor gamma, which is 1 minus v squared over c squared. So 1 over v squared minus c squared for v essentially equal to the speed of light is a very large number, because a small number is occurring in the denominator of the gamma, and because this angular opening goes like 1 over gamma, the opening angle is extraordinarily small. So the beams are extremely focused and therefore extremely intense. So this is basically a straightforward relativistic effect. If you were living in the frame of reference of the electrons, you don't see anything particularly interesting except radiation. But if you live in the frame of reference of the laboratory, you see that radiation focused into a very narrow beam. And because the X-ray, the electrons have been bunched, the beam comes out as pulses. These pulses are 100 picoseconds, actually, depending on how you measure, or less in duration. And the 46-meter separation means that they're separated in time by 153 nanoseconds. Now, the story is a little bit more interesting than that, in that the electrons are not continuously bent in the synchrotron ring, but they're bent in bent sections, and they're straight sections. So bent sections have bending magnets, which just exert a Lorentz force, which keep the electrons going around. But in these straight sections, there are another set of devices called undulators that are input in, which are banks of alternating north and south poles and permanent magnets. So in these straight sections, typically you would put one or two of these undulators whose length is about 2.5 meters, and they're made from a stack of neodymium iron boron magnets with a period of a few centimeters. So what happens is in this straight section, the electron pulse comes in, it oscillates back and forth like this, and it generates a focused beam of photons coming out. Okay, so that's basically generates the X-rays that we want to work with. Okay, so at that point, we've generated the X-rays, but we got to do a lot of more work. So the first thing we got to do is take this emitted X-ray pulses and basically isolate from them single pulses. That's for a couple of reasons, not the least of which is that the power that is being delivered by this incident beam is so phenomenal. It's similar. It puts the same amount of, it puts more energy into a square millimeter than that comes from the surface of the sun, for example. And it will not bore right through you, but it'll bore right through about almost anything else that's not properly cooled and handled. So we have to cut down the intensity of this beam to isolate individual pulses, and that's done through a set of choppers and shutters. Then what we do is we add a Ti-sapphire laser to this, a high power laser. So what it's going to do is produce 1 picosecond optical laser pulses with variable wavelengths. And what we're going to try to do is to synchronize the arrival of the X-ray pulse to the arrival of the pump pulse. Okay, so we're going to do that with a given time delay. That is going to then allow us to sample the response of the sample with a time delay that we can fix and generate a movie of X-ray diffraction patterns. So this would be a typical X-ray diffraction pattern that you might make from a polycrystalline sample. Okay, so that's the experiment. Now this process of isolating individual pulses is actually not really easy. And it is focused on the fact that we know where every pulse is in the synchrotron to within better than 10 picoseconds at any time. Okay, and what that means is that there's a master RF clock that drives the RF cavities that produce these pulses, and with timing to that master clock, we can locate in time where every individual pulse is. So what that means is that if we trigger based on the arrival time that we know of an X-ray pulse, if we trigger the optical pump laser by delaying or advancing its arrival time measured with respect to that same clock, that will give us a time delay that allows us to to bring out a movie of how a system evolves in time following excitation. And then the whole summary of this whole process looks like this. The optical pulse arrives at a known time. The sample very rapidly gets very hot. And so we can raise, within 1 picosecond, we can raise the temperature of the sample by 1,000 degrees or even blow it up if you want to do that. But because the pulse is very short, the temperature decays very rapidly, and then based on the arrival time of the probe pulse, we can sample the structure of this sample as the temperature decays and build up a map of the dynamics over as long a time period as you want, from tens or 100 of picoseconds out to milliseconds or even seconds if you want to do that. So this is all done on with the premise that there's one clock that everything, all the experiment is locked to, that allows that kind of the timing on a 10 picosecond time scale to be maintained for hours and hours and hours and days and days and days. Okay, so that's the experiment. Okay, so the one final thing before I start showing you some data here is that there are the beam itself that is being delivered comes in either a monochromatic mode beam or a pink beam. So the pink beam is what comes just off of the undulators. It's the pink, it's just the spectrum of the generated X-ray beam, and it can be monochromized if by putting a silicon single crystal monochromator in the beam. This is actually not so easy to do because there's so much energy in the beam that this has to be cryogenically cooled, and you have to maintain the lattice expansion in the silicon single crystal very much under control in order to make it operate as a good monochromator. So this is not very easy a thing to do. So if you use the pink beam and just do a standard sample, you get a very broad peak, what means you get a very intense beam, but poor resolution, and also a funky line shape. This is also a problem, that you get this funky line shape. But if you put a monochromator in the beam, then you get high angular resolution, but you pay for it by a vast dynamic reduction in the amount of photons. So if we take one of our gold platinum multilayers we want to study, if you look at this with a monochromatic beam, you see lots of structure, that's the blue, but if you look at it with a pink beam, you only have a hint of the structure that is there because of the loss of angular resolution. Now we knew that we were going to have this problem to begin with, and so we had designed our first experiments to actually be a little bit, to run with a monochromatic mode, but to recover the loss of intensity by rastering the sample. So what our plan was, or the proposal was, is that we would grab an X-ray diffraction pattern due to one area of laser X-ray overlap, then we would move the sample to a new one, repeat it again and again, and do this 1,000 or 10,000 times to recover the intensity that was in one pink beam pulse by multiple monochromatic pulses. And this basically just was an enormous headache to do. So it turns out that the problem, which we did not appreciate, is, although it's sort of obvious after the fact, that because you're bringing in your laser pulse perpendicular to the sample and the X-ray probe pulse is coming in at a shallow angle, if you don't move this sample over macroscopic distances in precisely the same plane, this region of overlap falls out of overlap. So you shift the region here by 10 or 20 or 100 micrometers, and now you're probing a region that wasn't excited. Okay, so this was a big problem that we had at the beginning. Just parenthetically, to give you an idea of how much power you can actually put into this laser pulse, you can just blow holes in the sample if you want to. These are just SEM images of some of those images. And the reason I show you this is not just to show you what you can destroy samples if you want, but the destruction produces very interesting structures in the film. And this is a problem that we're also sort of working on, but I'm not going to talk about today. But this has very interesting structure in the damage that's created by very high power pulses. Okay, so here's the scattering geometry. We bring the X-rays in as pulses. They scatter off the sample. They scatter onto a two-dimensional detector. So this is a very large two-dimensional detector. It's 34 centimeters on a side. Its initial purchase price is well over $1.5 million. And so what we do is we grab a tremendous amount of data in 2 dimensions of the scattered X-rays. And to just get everybody acquainted, this is the measured, this angle right here is just the standard Bragg angle, or twice the Bragg angle. And if we rotate this thing around, that corresponds to 1 ring on the detector, which will also, I will talk a little bit about measuring the angle psi away on that ring at a given Bragg angle, but measure it away from the normal direction. So that just gets summarized in Bragg's law, and how I'll plot some of this data in terms of the scattering vector, which is just 2 pi over d. Okay, so this is now what real data looks like. So this is a diffraction measurement taken with monochromatic X-rays, and it is on a gold platinum multilayer. So what you're looking at here is basically the ring on the detector. Every ring here is the same Bragg angle. But you can see that you have structure at a given Bragg angle depending on what the direction of the scattering vector is. So this corresponds to the scattering from the periodicity in the multilayer. This was what you'd call in the 1-1-1 direction of the film. And this is the 1-1-1 bar direction. This is the 1 bar 1-1 direction. And so you see scattering off this primary axis as well. These spots here correspond to the 200 diffraction peaks. And you can even see higher order ones up here, except they get cut off because of the position of the detector. Okay, now this is just in an as prepared sample, but you can see that this is just a case where we threw down 50 laser shots onto the sample and then just looked at the diffraction pattern. And you can already just visually see what the effect of the laser is. First of all, you're starting to wash out structure in this original peak here. And interestingly enough, you start producing an arc that connects this ring with this diffraction spot in this one right here. So this is actually a really interesting clue about something that is going on. So let me just show you now what we do. This makes what looks like a more standard X-ray diffraction pattern. So what I'm going to do here, this d here, and I apologize, I didn't multiply this by 2d to make it a scattering vector. There was a reason for that, but not important right now. But this dimension right here is essentially the scattering angle or the scattering vector. And that corresponds to moving vertically along one of these lines. Okay, is that clear? I hope to everybody. And then what we've done is to produce the intensity at that point, we integrate along this arc of constant Bragg angle. Okay, and so we integrate over this arc that generates what we call an on-axis diffraction pattern. That is, so before the laser fires, if we integrate this region right here, we get a standard diffraction pattern that just looks like it comes from a multi-layer. If we look at this region in here, before the laser fires, there's almost no intensity at all. That's this blue here. And if you look at integrate this angular region, let me see, where did my cursor go? If I integrate this angular region right here, then before the laser fires, I get this pattern right here. So here what you see is you're sort of starting to separate out platinum signal from a gold signal. Okay, now we hit the sample with 50 laser shots, but the dramatic change that happens is that we lose the structure here. You see that this has much less structure in this region of the diffraction pattern. We grow a lot of intensity in this intermediate region, what we call the intermediate axis. That's now this red curve right here. And if we also look off axis, we see a change in the off axis diffraction pattern as well. So even though it's not clear how much detail of information there is by looking at the image itself, and part of that is because I've basically processed this image on a logarithmic scale to help bring out some of the features. This is actually the real data, and there's a lot of data here. Okay, so the next thing, that was with a monochromatic beam, but the price you pay for using a pink beam, this is just reproducing that same data that I showed you before, But if you put down just one X-ray, one laser pulse that probe one diffraction pattern with a pink beam, you have a much more intense beam, but poor resolution. So if you look here, there's not a lot of structure that you can visualize when you see here. And so we needed to do something about that. So nevertheless, as we go forward, we want to fix that problem, but I wanted to actually show you, even with the poor angular resolution, the kind of information that can be extracted from these measurements. And so the first thing I'm going to show you is the diffraction pattern at, I call this minus 200 picoseconds before the arrival of the laser pulse. This is a sample that has not yet seen a laser pulse and is as prepared. That'll be black. Then 100 picoseconds after the arrival of that pulse, that gives us a diffraction pattern in red. 100 nanoseconds later, we have a diffraction pattern in green. And 1 millisecond later, we have the diffraction pattern in blue. And in fact, we have scores of diffraction patterns in between all these as well. So the qualitative information is that you see that the peak position at early time following excitation moves to smaller scattering vectors. That means larger d-spacings, and then recovers in time. Okay, so that is the dynamical problem that we're trying to resolve and to acquire and to study with this time resolved method. Now, even more interesting and unexpectedly to us was what looks like when we look at this intermediate region right here. So again, minus 200 picoseconds, the black curve here, very noisy because it's very poor resolution, and not that many photons even. You see that there's essentially no black signal here before the laser shot appears. But 100 picoseconds afterwards, you get a very broad signal, all right? Unmistakable and very broad. And if you've looked at many X-ray diffraction patterns, this looks all the world like the diffraction pattern of a liquid. It's enormously broad. And in fact, our supposition is that what you've looked at is in the first 100 picoseconds, the gold part of the gold and the platinum has melted by interaction with the X-ray with the laser beam, and we've grabbed that intermediate state. Then as time progresses, though, this very broad feature goes away, and 100 nanoseconds, we start appearing a narrow peak again, slightly offset from the first one, and that grows in time. So what we're looking at here is the resolidification of this molten state with modifications that have been induced by virtue of the alloying that has taken place between the molten gold layer and the hot but still solid platinum layer. So this was a first sort of interesting result that we acquired from these measurements. But the problem is that the resolution is very poor, and we thought we wanted to address that problem before going forward. And so that leads to kind of an intermission here, in which we designed and built and tested what we're calling a tunable multi-layer monochromator. So let me just show you a couple slides about how this works. So at the Advanced Photon Source, they are world experts in making X-ray optics. And they have one of the half a dozen best facilities in the world for making multi-layer structures that are so perfectly reproducible that they can be used as very high quality monochromators. And so in conjunction with Ray Conley in this X-ray optics group, he built for us a stack of molybdenum and silicon thin films, with very precisely controlled thicknesses. So in fact, even though I didn't write it here, this is 12.00 nanometers thick, and this stack is now reproduced precisely 250 times, almost with no variation at all. So when you scatter X-rays just off this stack, what it does is produce a very characteristic set of very narrow diffraction peaks that are arising from the periodicity in the stack, not from the the crystal, the separation distance between the crystal planes. And so our idea is that what we want to do is put this stack in the beam, and then we will use one or the other of these diffracted beams to be incident on the sample. And you can get an idea, and I'll quantify this in just a minute, that by which which order of reflection that you want to use, you can tune the intensity of the beam versus its bandwidth. That is to say, how monochromatic it is. I'll show you that result in just a minute, but we took this, these multi-layer monochromators that were built at Argonne, and Derek Allen in the machine shop in the physics department at the University of Delaware, we incorporated this into a precisely controllable double bounce configuration where the X-rays come in, they scatter off the first mirror, they scatter off the second mirror, and we have 3-axis control at the micron level over positioning these mirrors. So we can align everything to make the output beam come out precisely parallel to the input beam. Everything about this we have under very good control. This box can be temperature stabilized if you want to do it. You can replace the air on the inside with a light gas like helium if you want to reduce air scatter. So this is a box then that we carried to the advanced photon source and mounted in the beam there. Okay, now when you do that, what you gain is the following. Depending on which diffraction order you want to peel off, what you do is you go from a pink beam that has an energy structure that looks like this to the second order reflection that looks like this profile, then the third order reflection and the fourth order reflection. So what you see is the intensity goes down, but the bandwidth improves. So you have a higher monochromicity. More than that, what we do is we very much clean up the line shape. So this troublesome, funky line shape in the pink beam now becomes quite highly symmetric. Here I just normalized all the intensities. This is actually gives you an idea of how the intensity decreases. And then to summarize this, let me just point it to these chart without focusing too much on the numbers. In the pink beam, if the beam energy is 12 kilovolts, then the beam width is about 500 eV, and so that makes a bandwidth of 4%. The monochromatic beam only has an energy width of 1.2 EV, or a bandwidth of 1/100%. But you gain this monochromicity at a sacrifice of between 100 and 1,000 times in the intensity. So now, however, by putting this double mirror assembly in here, what we can do is we can tune the bandwidth from 500 EV to 130 to 60 to 35. And in so doing, there's a reduction in the flux. But even if we operate at a bandwidth of 60 EV, you can see that we have about 500 times the intensity in the monochromatic beam. And so that is the tunability that we wanted to try to optimize, to put into the beam and to try to make these measurements have higher quality. And so I'm running out a little bit late, and I want to end up a little bit without, so all I'm going to do is I'm going to try to show you 2 more data plots and then just cut to the end. This is the first set of measurements we did using that tunable monochromator. And so all this is a platinum thin film. It's 37 nanometers thick. And what you're looking at here is the platinum 111 peak. So the circles are the diffraction pattern without any previous laser interaction. Okay, so that's the black curve here. 100 picoseconds later, we get the blue curve. Very well defined, offset to smaller Q, larger D spacing. Then 300 microseconds later, you see that's the red. We've recovered exactly the original state. Okay. Now, if we do this with another laser pulse, then exactly the same thing happens again. So for these laser pulse energies of what order tens of millijoules per square centimeter, or more precisely, less than about 50 millijoules per square centimeter, the interaction between the film and the laser is completely reproducible, and we can probe that with time resolution. I'll show you that result in a second. But if the laser pulse energy is more than 50, we see the following. Again, here's the non-interaction. Then 100 picoseconds later, peak moves just like it did before, but now after cooling, it moves back to a position that it wasn't at the beginning. What this is indicative of the residual stress that was in the film was relaxed because of the interaction with the sufficient beam, the energy in the beam was sufficiently high to relax the stress state. On the other hand, that was just one pulse, that laser pulse that did that. If you now just go back to that same spot and do it again, you see now you start off where you left off, that was the red. Now you go to blue, but now you come back to the red. So now we're reversible again at a state of stress relaxation. Okay, so we were quite pleased with this. To show you in a little bit more detail, I'm going to show you all the data points that we took in time. The 40 millijoules, what we do is we collect a set of data points prior to the arrival of the X-ray pulse. And then you see this is a sequence, this is how the strain in the film evolves with time resolution. So this is over a very long period of time, but the time resolution is actually less than 100 picoseconds. So we have over many orders of magnitude of the time are tracking the dynamic response of this film to the initial laser pulse. The fact that if you use a larger excitation energy, that the initial state of the film is different than the final state of the film is just another way of saying that there was irreversible stress relaxation induced by the higher energy laser pulse that was done here in blue. So we've done a lot of sort of characterization of this. Let me not even bother about the next thing. That shows the essential features. And it was that tunable monochromator that we were scheduled to go back and do systematic sets of measurements when COVID shut everything down. So that's when in our next opportunity, that's what we're going to be doing. So let me just summarize this. And then we have a few minutes or as much time as anybody wants to ask questions if you'd like. My primary takeaway message is that national labs are just a fantastic resource for doing and studying really a huge range of scientific and technical problems. And it's worth emphasizing, because it's not maybe as widely known as it should be, that there are very large numbers of programs at all the national labs for undergraduates to spend summers there, for graduate students to spend more extended amounts of time, for faculty to visit and to interact with the staff and the scientists at the laboratories. And they are more than willing to try to facilitate that in any way they can. So there's a variety of programs that your students can apply, you or your students can apply to, that are just provide amazing resources for studying a variety of problems. So that's a broad takeaway message, but also I think we have successfully demonstrated that we can do ultra-fast time-resolved measurements associated with irreversible processes like atomic transport, and we can do this with a time resolution better than 100 picoseconds. And because this technique is now available, if you have some ideas about what you would like to do with 100 picosecond time resolution, then new ideas are always welcome. Okay, so we continue this work, although we haven't been back in more than a year and a half. We continue to work on making multi-layered diffusion couples. We work on our chemical techniques for doing zero-dimensional core shell mixing, and we have other things that are going on as well. One of the sort of interesting thing is we developed a technique for taking aqueous solutions of small nanoparticles and preparing single layer films approaching 100 square centimeters that we can use for these kind of studies. So we have sort of an interesting way where we can make very large areas films, but they're made up of one thickness of 100 or 50 or 200 nanometer diameter film coating that surface. Also, there's a huge computational issue that's associated with this. And so another one of the things that we've been focusing a lot on in the last year and a half is trying to develop computational methods for extracting information from these diffraction images. And so we're doing this by one technique we're working on is called reverse Monte Carlo. And the other one is to apply artificial intelligence type methods. So we've built very deep neural networks that we've been training, that we've been trying to teach to understand, to allow us to extract information from these films. And finally, nothing ever gets done without a lot of people being involved, and I really want to give the credit for that now. So at the University of Delaware, my colleague's Matthew DeCamp. He's in the physics department. He's the laser expert and one of the laser experts in our department. His office is next door to mine, and it was our discussions that sort of led to this to begin with. For many years, I've been collaborating with Klaus Theopold, who is an exceptional synthetic chemist in the chemistry department. He has helped with all of the work on chemical synthesis that we've been engaged in. And each of us has a graduate student that has worked on this. Brian is my student. Aaron has worked with Matthew DeCamp. And Gia has been the chemistry part of this team. There have been technical staff in the department, Jerry Poirier, Robert Schmidt, Derek Allen. They've helped out a lot too. A colleague at Johns Hopkins who is also a co-investigator on our NSF grant, Tim Mueller. He has been, his expertise is in computation, and we've taken a lot of advantage of him. At Argonne National Laboratories, Anthony DeCharia, a former graduate of our department, Robert Henning and Ray Conley, they are staff scientists. And of course, we want to acknowledge the National Science Foundation for funding this, or for providing dollars, and for Argonne National Laboratory and the Advanced Photon Source who have provided the facility. So typically national labs aren't going to give you money. You got to get there and do that on your own, but they will provide all the technical facilities, all the clean rooms, all the chemical synthesis labs, everything there will be available to you when you make a visit. So with that, that's where I want to end up. Let me just say I'm happy to talk about questions as much for as short or as long a period of time as anybody has. And hopefully, as Winston Churchill said in 1942, this is not the end of this story or even the beginning of the end, but maybe the end of the beginning. So with that, excuse me, let me just stop. And if anybody has any questions, please ask. Anything's fair game.
Well, that was a great talk, Carl. Thank you very much.
Thank you.
We're open to questions and discussion topics. We have a new professor here who's working on solid state physics, and I think he might be a great person for you to want to meet.
That would be fantastic. Yeah. So, and I also particularly encourage students who are often very shy about talking. If you have any questions, I'm very much interested in what you have to say or any questions you might have as well. So yeah, please, nobody be shy.
I think Abal, he's left, right, Holger?
Right, I don't see him on anymore. He was here until recently.
Right, he was here. I thought that might be a great introduction to Carl, since there's a lot of overlap. Okay.
Well, anybody that's interested and wants to contact me, I'm always interested. I mean, I'm fine to do that as well.
Okay. We're open to questions. It's a little bit outside of my knowledge, but if I ask a question that's not relevant, let me know. But
yeah, what I say is I always like to, let me jump in and say, I don't like questions being prefaced that way, because they're often the profound, difficult questions to ask that are coming from people. Right.
Well, I mean, Norman Ramsey was doing something with pulsed light. Is that similar to what you were doing?
So Norman Ramsey, no, as far as I know, Norman Ramsey was, he was an optics guy from beginning to end, as far as I know. Okay, yeah. Now, of course, he's a very big name, smart, fancy guy. And so I may have overlooked something. But my knowledge is, so let me just say maybe a little bit of background to that. So this technique is a ultra fast pump probe technique, but it's ultra fast optical pump X-ray probe. But even before this technology was developed, there is a very sophisticated technology that continues to this day that is ultra fast optical pump optical probe. So typically what one would do, and this is an in-house experiment. So what one does is you use, say, a picosecond laser or faster, but you split the light into two paths. One of the paths you direct onto the sample to optically excite it. The second one you time delay through a optical fiber of a certain X number of meters to get time delay, and then use that other half of the beam to probe the optical response. So for things like electronic transitions, doing chemistry, in which there is a dielectric change, or there is a reflectivity change, or there's something that is changing that can be probed optically, that technique is very well developed. It's when you try to change the probe from a optical pulse to an X-ray pulse that you almost have to move to a national laboratory to do that. Although there are some in-house optical pump X-ray probe experiments that people do as well. But that's kind of we can talk about that as well, but that's kind of a niche kind of thing to do.
Right. Yeah, I don't know if you overlapped with Norman Ramsey, because he's from Wichita also.
Actually, I didn't even know that.
Oh yeah, he's from Wichita. I met him when I moved here and took over as chairman of physics, and he was probably he never got his degree from us. He only spent the first year here.
I see. Okay.
He went off to Harvard.
Yes, exactly.
Bachelor's degree.
Made a big name for himself, right?
Make a big name for himself. He has since died, you know.
Yes,
course.
I did know that.
Yeah, but he was actually originally from what's the name of that town? It's like halfway between here and Lawrence, because his father was in the military.
Okay, yeah, I didn't know. I'll look into that. Yeah, I didn't know that he had that background.
Yeah. So yeah,
yeah, that's interesting.
Yeah, I reached out to him, and he gave a talk in the first year I was here. It was kind of fun. But I just remembered him talking about pulsed lights as a way, and your pulse thing just reminded me of his talk in a lot of ways.
Yeah.
Okay.
So you talked a lot about, oh, Matt has a question, but maybe I can ask quickly. You talked a lot about gold and platinum. What I missed is why there's a particular interest in those materials, or that.
Yeah, exactly. So there is nothing at this stage per se, but the reason they were chosen is because we know that we can very effectively couple light into gold and into platinum. So what we wanted to do is to have well, there were a couple of criteria. First of all, because they are very easy to prepare chemically, because they're easy to reduce from metal salts. Okay, so they're easy to do chemistry with, to make cores and shells. The second thing is they're very easy to prepare films of by magnetron sputter deposition, which is what we do, and we can make very high quality flat films with that. And then the next thing is what I mentioned before, is that for gold and platinum, you can couple light into optical light in the 400 to 800 nanometer wavelengths very effectively. So you don't scatter an enormous amount of light off, and you can really jack you can get the energy to be absorbed and jack the temperature up in the sample, well, as much as you want to go, including to the point of just blowing the sample up. In fact, it's a little bit interesting. I didn't say that, if I just take a second, our first idea was not to raster the sample, but to make nanoparticles in a solution and do a free jet. We would squirt them in a very thin jet, and then there would be no container, it would be containerless, and we would do the X-ray beam like that. So that actually didn't really work very well. And then the next thing we thought to do is rather than make the jet, because there are jet instabilities that you have to manage when you do that. Well, of course, anybody that thinks about it would know, but we just thought, well, we'll just do it. Then we thought we'll take an optically thin tube of polycarbonate and we'll pump the liquid through and the X-rays won't see it. And I even was very careful. I thought that the X-rays would not interact with the polycarbonate or anything like that. We go there, no signal, nothing, when we did this. And then we start looking around, but it turns out that there's the laser energy is so high that there are nonlinear effects that lead to the energy being dumped into that polycarbonate, and it just blew it up. So it just you know, in 100 picoseconds, the sample and everything else is gone. It just blown up, and we're looking at these monitors and wondering where the X-ray beam went, right? And there's just no sample anymore. So you can really blow things up, and gives you an idea of how careful you have to be. So the safety protocols are significant, very, very significant. Right. Yeah, so I think there was another question, maybe. Yeah. What did Dr. Rowe, or did you have? You looked like you were trying to say something at one point, and I interrupted.
I was just wondering about the. I've only worked with resonant frequencies, and is there any type of correlational data that you can attribute the resonant frequencies mechanically to these dissociation type of responses that you see in light scattering?
Yeah, so there's a very beautiful, well, I think this is related to what you're saying. There's a very beautiful kind of measurement that one can do, which is to take just a thin film, just like this platinum, and you hit it with a single, say, picosecond optical pulse. Okay, so what happens is that the energy is initially deposited into the electronic degrees of freedom, and then decays in about 1 picosecond into the nuclear degrees of freedom. But it comes as one high temperature pulse, and that excites a coherent optical, a coherent acoustic phonon, and the film rings like this. And it rings with a period that's characteristic of the thermal transport across the thickness of the film. And you see this wave bounce back and forth and back and forth. And in fact, this is a very powerful technique for studying a variety of kind of effects that are sort of fundamentally mechanical, but are intimately connected to the electronic degrees of freedom and the structure of the sample. So they're very beautiful measurements that can be done this way.
Oh, very good. Yeah, interesting.
So it turns out, unfortunately, we don't quite have the time resolution to see that, because the characteristic time, so for films that are of the order of tens of nanometers thick, the period of that oscillation is of order 10 or 20 picoseconds. And we just don't quite see it, right? So you have to use a shorter pulse in order to see it.
I think Professor Musa and Richard Traverso have their hands raised. So, Matt?
Yeah, I have this maybe is kind of to the side of your talk, but I know there are at least 5 DOE supported light source labs across the country. I'm just curious, what is the feature at APS that makes you want to do your work there, and how does somebody in your field decide which lab to go work at, and what are those experiences like at the different labs?
That's a really good question. So in the United States right now, there are 2 third-generation light sources, and over the world there's probably 50 of various levels of sophistication. Okay, now, but they are structured very differently. So the light source at Argonne National Laboratory is constructed to produce electron bunches that are spaced, as I said, by about 150 nanometers in time. Now, the light source at Brookhaven National Laboratory is called the National Synchrotron Light Source -2, which just came online basically a few years ago as a follow-on to version 1. It spaces the X-ray pulses, the electron pulses much closer together. They're just a few nanoseconds separated. But because of that, it is impossible to mechanically separate and isolate one pulse at a time. So to sort of in one way answer your question, if you want to do time-resolved X-ray diffraction and you want to do it at a synchrotron, it has to be done at Argonne, and it can't be done at Brookhaven. Now, I alluded to this. The detector group we're sort of collaborating a little bit with at Brookhaven is designing fancy X-ray detectors that they claim will provide 1 nanosecond time resolution just by the speed with which they can grab a diffraction pattern and read it out. Okay, so this turns out to be a very difficult problem. So we got a beam time allocation to go there and have them install that detector on our experiment. But, well, it turned out that when they realized that that basically to make that detector work, they have to have like 5 people associated with the experiment. And they didn't want to release 5 staff members for our dumb little experiment, right, to try this thing out. So we went there, we did some preliminary stuff, but so that's the decision that you have to make. Now, you also, in Europe, the ESRF, the European Synchrotron Research Facility, is basically a mirror image of the APS. It's an 8 GeV ring, it's almost identical, but it's also, because there are many experimental stations associated with it, they optimize for doing one class of experiments versus another. And so there's just an enormous range of things to do. So it's very interesting that when you get allocated time we typically get it in 4-day increments. And when you get 4 days, that means you run 24 hours a day, which means that you're buried in this windowless, cavernous place at 2 o'clock in the morning and 3 o'clock in the morning, and you're exhausted. And if you're interested, I can tell you where I thought that because of this, I almost destroyed my career because of almost destroying that $1.5 million detector by a mistake I made. But it didn't happen, but I can tell you that story too if you're interested. But as you walk around, so at the APS, there's about 40 places around the circumference where the beam is brought out. So there's experiments that are dedicated to biology, to magnetism, to imaging, to high pressure physics, to everything under the sun. But when you walk around, everybody just has their posters up outside. And it's just fascinating, the range of, I see a future astronomer there. I hope that in the background. So it's just amazing, the range of things that are done. It's a fascinating, fascinating place to be. So, anytime you can go there, just ask for a tour if you're there. They're with time, they're happy to accommodate that. If you want to take students there just to visit, they're more than happy to show you around. It's just a phenomenal place to go and to work.
Great, thank you so much.
Yeah, actually, so in about a year, it's being shut down, okay? And it's being rebuilt. What's called APS-U for APS upgrade. So this is in excess of another $800 million that's going into it. But one of the big issues that even an ongoing fight is that what they want to do is to pack the electron pulses tighter than what they are now. So rather than running in what's called 24 bunch mode, they want to run at either 48 or 96 bunch mode. Now, the trouble for the time-resolved community is that it's still just possible to mechanically separate individual pulses if they're separated by 75 nanoseconds rather than 150. That's really hard, but still possible. okay? But if they go to the next factor of 2, which is which builds the beam current, which is what they want to do, it goes to now a separation of 30 or 40 nanoseconds. You can't do that really. And that means that if you want to do time resolved measurements, you have to operate in a structure that they don't want to, they only want to use 10% of the time or 20% of the time. And therefore the time you have available to do these kind of measurements is much less. So that's sort of an ongoing conflict that's trying to be worked out now. But we'll see. The upgrade is supposed to take 1.5 years or so. And it should be just absolutely beautiful when it just, you know, you spend $800 million on something and it's really nice.
Sure.
All right.
I think Richard has a question, I think I can throw to him.
Yeah, sure.
Yeah.
Anything else?
Yeah. Yeah, this was a great talk. A lot of the intro stuff, I'm going to have to look back and show my basic calc-based electromagnetism students. It's good examples of the synchrotron.
Actually, if you don't mind, if I just interrupt you for a second, then we go on. If you're interested in doing something like that, let me see if I can put my hands on it right here. There is a little thin book you can buy that's called Synchrotron Radiation, an Everyday Application of Special Relativity. And basically it is a discussion of electromagnetism and special relativity, but in the context of synchrotron radiation, which is one of its most impressive manifestations. And it's a nice little book. It's not mathematically complicated. It's
Sure.
just a nice little book that you might want to look into at some point if you want to pursue that line of thought. But I'm sorry to interrupt. Go ahead.
Yeah, no, that's good because our physics textbook only has like a couple of paragraphs about it. Yeah, what I was thinking is that when you're talking about these optical probes, I mean, I've done some like intro reading about second harmonic generation and how when you send in 2 lasers of some specific frequency, they can excite the polarization states in the dielectric and then pump out the laser of twice the frequency, and that's the famous blue laser that was discovered in like early 1960s. I'm wondering if this X-ray, if this same sort of effect transfers at that frequency level, at the X-ray level, if there's some sort of like doubling or something like that.
Yeah. Actually, I don't think so, but I don't know for sure.
Sure.
Yeah, so I'd have to think about that, but that's an interesting question. So actually, again, if you just have a minute or so, so another sort of semi-related question is, well, I made the point that we're isolating single pulses mechanically, but that requires, that is an impressive operation because you're spinning blocks of metal at very high speeds with shutters in them to open and close it. And when they fail, you're hundreds and hundreds and hundreds of thousands of dollars out of luck. But having said that, so the idea comes up is, that's kind of stupid. Why do this mechanically? Why not do it optically? And so why not take a birefringent crystal and hit it with a fast laser pulse and change its index of refraction in just such a way that it diffracts allows the X-ray beam, it shuts the X-ray beam off and allows it to go depending on how you've excited this crystal with an optical pulse. So people have done this and this works, but for reasons that I am not completely clear about, is never really proved feasible to do on sort of a routine basis. So if you can think of an optical way to chop a beam at very high rates, that would be a very nice thing to know how to do if you could do that.
Yeah, thanks. That's a great answer.
All right. Well, we are a little bit past our usual time. Also, some people have logged off, but certainly if there are any more questions.
Yeah, like I say, I'm happy to stick around, but that's completely up to you. I'm flexible.
All right. Well, maybe we thank you one more time for a very nice presentation, and thank you for your time. And I'll end the recording here, but we can chat a bit more if you like.